Non-Euclidean Geometry by Roberto Bonola. Chapter 1. The Attempts to Prove Euclid's Parallel Postulate. Section 5. The Greek Geometers and the Parallel Postulate. Section 5. Another very old proof of the fifth postulate, reproduced in the Arabian Commentary of Al-Nirizi, 9th century, has come down to us through the Latin translation of Gherardo da Cremona, 12th century, and is attributed to Aganis. The part of this commentary relating to the definitions, postulates, and axioms contains frequent references to the name of Sambalicius, easily identified with Simplicius, the celebrated commentator on Aristotle, who lived in the 6th century. It would thus appear that Simplicius had written an introduction to the first book of Euclid, in which he expressed ideas similar to those of Geometers and Posidonius, affirming that the fifth postulate is not self-evident, and bringing forward the demonstration of his friend Aganis. This demonstration is found upon the hypothesis that equidistant straight lines exist. Aganis calls these parallels, as had already been done by Posidonius. From this hypothesis, he deduces that the shortest distance between two parallels is the common perpendicular to both the lines, that two straight lines perpendicular to a third are parallel to each other, that two parallels cut by a third line form interior angles on the same side, which are supplementary, and conversely. These propositions can be proved so easily that it is unnecessary for us to reproduce the reasoning of Aganis. Having remarked that propositions 30 and 33 of the first book of Euclid follow from them, we proceed to show how Aganis constructed the points of intersection of two straight lines which are not equidistant. Let AB, GD be two straight lines cut by the transversal EZ, and such that the sum of the interior angles AEZ, EZD is less than two right angles. Figure 4. Without making our figure any less general, we may suppose that the angle AEZ is a right angle. Upon ZD, take an arbitrary point T. From T, draw TL perpendicular to ZE. Bisect the segment EZ at P, then bisect the segment PZ at M, and then bisect the segments MZ, etc., until one of the middle points, PM ... falls upon the segment LZ. Let this point, for example, be the point M. Draw MN perpendicular to EZ, meeting ZD in N. Finally, from ZD, cut off the segment ZC. The same multiple of Zn as Ze is of Zm. In the case taken in the figure, Zc is equal to 4 times Zn. The point C thus obtained is the point of intersection of the two straight lines AB and GD. To prove this, it would be necessary to show that the equal segments Zn, Ns, etc., which have been cut off one after the other from the line ZD, have equal projections upon ZE. We do not discuss this point, as we must return to it later, page 11. In any case, the reasoning is suggested directly by Aganis' figure. The distinctive feature of the preceding construction is to be noticed. It rests upon the implicit use of the so-called postulate of Archimedes, which is necessary for the determination of the segment MZ less than LZ and a submultiple of EZ. Non-Euclidean Geometry, a critical and historical study of its development. This book was written by Roberto Bonola, professor in the University of Pavia. It was published by the Open Court Publishing Company, Chicago, 1912, and is now in the public domain. Read by Jim Renholt, with programming and illustrations by Jim Renholt, 2019. Thank you for listening.